I will begin with a word of prayer once I get up here. Dear Father, we thank you for this day. Again, I thank you for this class, these students, and just ask you to bless our work today. Help us to glorify you what we do and to enjoy the weekend, which is about to start, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me just review a couple things we derived like previous classes. First of all, we worked out that if we have a rod rotating around its end, the moment of inertia works out to 1/3 ml squared. Then we also took that same idea and looked at it as, rotating around the middle. We said, well, that's L over 2 and L over 2, so those are rotating around the middle. We can just double up the last example, appropriately modify it, of course, to half the mass and half the length, and that ended up giving us 1/12 ml squared. So we had that, right? Then I talked a little bit about the moment of inertia for like no picture, but if you just have a cylindrical shell, all of the mass is radius, distance r away from the rotational axis, right? So the moment of inertia is just mr squared. On the other hand, if we have a uniform solid cylinder of radius r, we worked it out and we got that the moment of inertia, if you've got a solid cylinder of radius r, is 1/2 mr squared. And we had to use calculus to do that, right, like this. 1/2 mr squared. And then we thought about a thick cylindrical shell. And what we did there was we subtracted the moment of inertia of the missing piece from the moment of inertia of, the shell of the cylinder of radius b. And that, it turns out, works out to 1/2 m a squared plus b squared. If you look at that, there's this one example contains both of the previous examples as limiting cases if you think about it. And the limit that a and b both go to r, this becomes 1/2 mr squared plus r squared, which is just mr squared. That's the cylindrical shell example, if a and b are both going to r. On the other hand, if we put a to 0, we're just back to 1/2 ma squared, which would be the solid shell. So this formula naturally picks up both of the previous examples as special cases. Now, the next one, that's the remark is just another way to derive it, which I think is the way we did it. The next thing that we need to know about, moment of inertia for a sphere. We can take the sphere, right, and we can slice it into disks of mass dm, and we'll see the picture on the next page here. So we got, well, actually, I think I don't have a picture for the disk method, so if you don't mind, I'm going to skip down and do the shell method instead. So here, if I wanted to calculate the moment of inertia for a sphere, I can divide it up into a bunch of cylindrical shells of radius r, right, where r is ranging from r equals to 0 all the way out to big R. And the height of the shell, it's a function of both the radius here and the radius of the sphere. You notice r squared plus h squared is equal to big R squared. So the height of the shell would be 2h, and h would be the square root of r squared minus r squared there. And so to calculate the moment of inertia, I can just add the inertia, moment of inertia for each shell, which I'm getting to here. The way I did it, though, was I found the mass of the shell is given by this. So I've got 2 pi r times 2h. That's the area of the cylindrical shell if you just laid it out flat. The thickness would be dr. And then rho is the mass per unit volume, so the density. So density times the volume gives me the little bit of mass in that shell. And then I take this, and what's the difference between this guy's and this guy's? What am I doing? Moment of inertia, how did we calculate it? We calculated by the integral of r squared dm, right? So this is my dm, and you notice there's an r squared here, right? So r times r squared, this r times r squared gives me an r cubed, and I have to integrate from 0 to r, see, because there's a shell at each little radius from 0 all the way out to r, and that gives me the totality of the sphere, which puts me up against this pesky integral right here, which isn't too bad. I mean, compared to some of the stuff Dr. Sprano asks you guys, you know, or Dr. Joseph, whoever you've met your fate with, you've seen uglier integrals in Calc 2 for sure than this, but you work it out, and lo and behold, you get 2/5 mr squared. I think the integration with the disk method works out a little bit easier, but whatever. Anyway, something to remember, the moment of inertia for a solid sphere is 2/5 mr squared. The next example is for a conical top with a uniformly distributed mass m. So here we're just talking about a cone, all right? So like a cone. And we don't need to work out the details, but it turns out that if you take a cone and you spin it around the axis of the cone, all right, the moment of inertia for such a thing is 3/5 mr squared. And let's see here, what else? Spherical shell, the spherical shell, the moment of inertia for a spherical shell, I think genuinely involves methods of calculus 3. I don't think I would ever test physics 231 on the derivation of the cylindrical shell one. Like the spherical shell, I mean the solid sphere, that I might test on occasion, but like the spherical shell, it's genuinely calculus 3. So you calculate the mass per unit area is constant in a uniform shell, but the total area of a spherical shell is 4 pi r squared, right? Surface area of a sphere is 4 pi r squared. We should know this. You'll derive it in Calc 3. But so the total mass divided by 4 pi r squared is the mass per unit area. So that's dm ds, where ds is the infinitesimal surface area element. It turns out that the infinitesimal surface area element works out to r squared sine phi d theta d phi. And so basically that times sigma gives me the mass in a little smidgen of the surface. So this here, I've got sigma ds times r squared. This gives me the little bit of inertia from that little bit of surface. And then I integrate that over the whole surface, and lo and behold, I get 2/3 mr squared. Compare that to the solid sphere. The solid sphere had a moment of inertia of what was it? 2/5. Which is bigger, 2/3 or 2/5? 2/3. Does it make sense? The moment of inertia, everything else being the same, right? Radius and mass being the same. Does it make more sense that a spherical shell has a larger moment of inertia than a solid sphere? Think about it, right? You've got more of the mass further away from the radius of rotation, right? That's why it's got a larger rotational inertia. All right. This one, so we're almost done with this diatribe of calculus, but these things matter. I mean, this is the basis for our other examples. Here, I need to get an adapter. If I'm not careful, all of a sudden I'll run out of batteries. The worst problem is the computer will shut itself off mid-talking because it's into power mode. So the example I'm looking at right now is very relevant because it's very much related to one of your homework problems where I have questions about like a wagon wheel. So one of you guys asked me like the spoke, is a spoke a radius or a diameter? Which is a good question, you know. But when I talk about a spoke in here, I am thinking of just the radius, not a diameter, right? So it's not the full circle, it goes from the center out to the rim, is what I'm thinking of a spoke being. If that's technically incorrect, I'm sorry, I'm not a cyclist, or even a bicyclist. But so find the moment of inertia for a wagon wheel about its center if it has 6 spokes, each mass m, with a rim with mass m at radius r. The spokes have mass 2 kilograms each, and the rim has a mass of 40 kilograms. The wheel has a radius r. How much kinetic energy is stored in the wheel as it rotates at 360 RPM? So let me draw a picture of this to make it a little bit less mysterious. So I'm saying the rim, all right, I don't really have any dimensions for the rim, right? Although if I did have dimensions for the rim, we could calculate the moment of inertia more precisely, couldn't we? Because we have the thick cylindrical shell inertia formula. We could use that, right? 1/2 m times a squared plus b squared. But I don't. I just tell you that the rim is at radius whatever it is, right? And then, so you got this rim, and it's got a mass of, what was it, 40 kilograms? And then how many spokes did I say? 6. All right. So I'm kind of zoomed in on the board at the moment. I should probably zoom out a bit. Then, so, I mean, I'm assuming they're, placed symmetrically. I'm not very great at drawing that, but, whatever. There's like, that was an attempt at sad attempt at 6 symmetric spokes. Very, very sad. But he has 6 of these, right? Do I have 7?
That's not a peak.
1. No, there's 6. I've got six spokes, but I did mean to. Yeah, that's just part of the diagram. Anyway, so is this bothering you guys? I can try again. This is very important to the physics that I get this picture right. So let me try again.
Just draw a straight line across.
Straight line across won't do it. There's no diameter if they're placed symmetrically. But if I did one here, and I do one here, and I do one here, and then I divide those, we'll be pretty much where we need to be. Oh man, I still messed it up.
I think it's better.
Oh, that wasn't where it was. I'm gonna have to try. You guys have driven me to it. I'm gonna just keep doing this until I get it right.
What if you
This is all we're gonna.
What if you just draw
3
three
lines,
diameters?
3 diameter lines.
This is all we're gonna do.
3 diameters.
So I'm gonna start at 0 degrees,
There should be
120 degrees,
Okay, now
240 degrees. So 60 degrees, 180.
Oh, wait. That's better. It's the top right one.
That's all you're gonna get. Deal with it.
Straight one across the middle.
You can go give your own physics lecture later. This is the one I'm giving. So, all right. So six silly spokes. And so what's the moment of inertia of? And these have mass. 2 kilograms. Thank you. So 2 m equals 2 kilograms for each one of those. All right. I'm going to start. So the point is the total inertia, moment of inertia for such a wheel, we can get by adding the moment of inertia for the rim. Curse the cursor. Let's see here. There we go. The moment of inertia for the rim, which is easy, mr squared, right? Because that's all distance r from the rotation. So it gives us the mr squared term, the rim. And then over here I've got 6. And why do I have a 1/3 mr squared? Little m. Because they're rotating around their endpoint, right? So we're back to the 1/3 ml squared we derived the other class. So that would be the total moment of inertia for this wagon wheel. And so I plug in the numbers, I get 44 kilogram meters squared. Kinetic energy is 1/2 I omega squared. Converting my omega to radians per second, lo and behold, 31.27 kilojoules. So there you go. So if you guys don't mind, I'm going to keep using the projector today, partly because I have theoretical results I want to share with you that, yeah, maybe it would be fun to see me write them out and derive them on the board. That would be lovely, but that would require me having a brain that was working today, which I don't have because I took my daughter to the Narito Symphonic Experience in Richmond last night from 7:30 till 10:20, and I arrived back at my house about 1:05. So I'm slightly, yeah, I really would like to just go home and take a nap. That would be great. So would you? Yeah. But the good news is I do have these notes, and we should try to digest them together. And hopefully at the end of this, I will actually work an example on the board, which will be hilarious because it's going to be full of mistakes. I guarantee it. So if I have this picture, this is the parallel axis theorem. So the parallel axis theorem says that if you have an axis which is parallel to the center of, so you have one axis that goes through the center of mass, all right? And you've got another axis which is parallel to the center of mass, then the moment of inertia relative to the parallel axis is equal to the moment of inertia relative to the center of mass axis plus mh squared, where h is the distance between the parallel axes. So this gives us a way of finding new moments of inertia from old, but you have to make sure that your moment of inertia is with respect to a parallel axis. Like here's an example. Barbell with a pair, if we have let me draw the picture. So I've got a barbell, distance L. So I'm drawing somewhat very big bells. All right, so something like that. My distance, what's the distance between spherical masses, radius r, separated distance L? So like this distance is L, and these are supposed to be spheres. Oh well, I tried. So this distance here, r, right? So we got mass m over here. The question is, what's the moment of inertia of this barbell? So if we don't have any, if we didn't have any particular specs on the size of the, the spheres, then we'd be stuck with just treating them like point masses, right? But since we do, we can use the parallel axis theorem, you see? Because if I have, here's my center of mass axis, right? And I'm trying to think right now. That's probably a bad idea. So my h is L over 2. Yeah. So so this distance is the distance between the parallel axes, which is h. And so the moment of inertia around the center of mass is, what did I say, 2/5? I can't remember. Is it 2/5 mr squared? These are solid barbells, right? That's what we got, 2/5? Yeah. So I do this plus h is L over 2 here. So plus...
Big R or little r for inertia?
Well, I said the radius of the barbells was big R. So...
Previous examples, we showed that inertia was like for the cone, it was little r squared.
What would little r be here? I don't know what you mean.
I'm just asking like...
Big R and little r don't have a separate meaning in and of themselves. They're labels we put on physical problems. So, like the meaning of little r and big R is not reserved in as much. I mean, little r tends to be a polar distance, but that's kind of all I can say. Sometimes it's a spherical distance in physics, like sometimes r is the square root of x squared plus y squared. Sometimes little r is the square root of x squared plus y squared plus z squared, truth be told. Sometimes it's the square root of x1 squared plus, let me not start this. Where was I? So mh squared, but the h is what? L over 2, so we've got m L over 2 squared, right? Oh man, I'm sorry. So this is the this is the center of mass, and then my parallel axis theorem says that I do what? The moment of inertia on the parallel axis is equal to the center of mass, moment of inertia plus mh squared. So this tells us that the moment of inertia we want here is twice times 2/5 mr squared plus m times L over 2 quantity squared. Why is there 2 there? Yeah, there's two dumbbells. What are these things called? Why are they bells? I have no idea. But don't look like bells. But yeah, and so we're assuming in this setup that the bar which connects the bells is like massless, which is kind of dumb, right? What if you wanted to make that not silly? You could also add together. You could also add what, like the mass of the bar, and if I did that, what would that be? I'll add that to this example here for us. Like here. What do you want the mass to be?
15 kilograms.
Oh. Hideous. All right. I was hoping for like a letter, but all right. So plus 15 kilograms. It's just so. It's all right. Fine.
In this example,
And then what?
in this example here, where is, like, I know we have this parallel axis of rotation, but like, if you think about this like physically, when you like have a barbell, like they're flat like this, and
Oh, these are old-timey spherical barbells.
oh, spherical.
Yeah, these are spherical. These are not like discs. Like, this is not like an actual weight set that you might find in the gym or something. Where you've got those, yeah, like you said, they're kind of flat discs of sorts, right? So, fair enough. You should envision someone with like a properly waxed handlebar mustache lifting this, that kind of thing. I guess I could fire up the most recent ChatGPT and come up with an appropriate cartoon for this, but I haven't had the time. This is not right, though, because that's just a mass. What else do I need here? We're calculating moment of inertia about the center of this barbell, right?
So that would be n over pi r squared.
We've got a rod. I'm just treating this as if it's a rod, okay?
1/2 mr squared.
I got to vote for 1/3. Any other votes?
It's solid, right?
Solid, yeah. We're going to think of it like a square, just a plain old rod. We don't really know anything about its cross-sectional, what's the words? We don't know anything about its cross-sectional shape. We'll assume that it's uniform mass per unit length. We know that. It's rotating around the center. Did we use 1/3? We do not use 1/3 for center rotated rod. We use what? 1/12. Yeah, 1/12. So 1/12. 1/3 is a good idea, though. That's just 1/3 is what we use in this example because the rods are rotating around their endpoint. Here, if we consider the axis of rotation to be the center, then the rod is rotating around its center, right? If I asked you what the moment of inertia was for this barbell, instead of around the center, around, let's say, the axis of one of these spheres, we could also calculate that, right? Now a smart way to calculate that would be with the parallel axis theorem, because this thing we're calculating right here is actually what? This is actually the moment of inertia of the barbell with respect to its center of mass in total, right? Okay, enough of this. Let me move on here. Again, I have a link in the notes there to the derivation of the parallel axis theorem in a previous notes that I wrote, so you can look at that if you want. Or you could read about it in the book, I suppose. So next up, I want to talk about composite motion, which is to say that we've got a combination of translation and spinning, all right? And so basically, it turns out we're going to derive, the next about page and a half of my notes here, derive this formula, namely that the kinetic energy for a mechanical system formed by a rigid body translating and rotating corresponds to two pieces: the translational kinetic energy, which is 1/2 the total mass times the velocity of the center of mass squared, plus 1/2 I omega squared, which we call the rotational kinetic energy. So here's a picture. We consider a typical infinitesimal mass dm, and so here's my rigid body. It's moving through space, and as it's moving through space, it's rotating. All right, and it's rotating around some axis of rotation like that. So if I think about this little infinitesimal mass dm, that's a typical part of the body, and its position in space is given by the center of mass position plus its relative position relative to the center of mass, which I called r prime. So it's at r plus r prime. And here's a zoomed in picture of this, my rotation axis being up down. You've got one piece, r prime has two things, right? On the one hand, it has the part which is parallel to the axis of rotation. On the other hand, it's got the component which is perpendicular to the axis of rotation, right? Only the perpendicular piece really directly ties into the rotational speed, right? If this r was equal to 0, the dm wouldn't even really be engaging in rotational motion. It's just spinning in place. That doesn't really, if it's a point, there's no rotational kinetic energy there. So if we calculate the velocity with respect to r prime, we'd have ddt of n plus r, but n is not changing because n describes how far the little bit of mass is relative to your origin in the rigid body. So that's not changing. It's only the r vector here, which is changing as you're going round and round and round. All right. So anyway, if I let gamma be the actual position of the little dm, if I differentiate gamma with respect to time, I get two pieces. I get the center of mass velocity and the relative velocity. But the relative velocity is actually just the part of the relative velocity which is interesting is, well, I mean, this is the whole relative velocity, but it turns out that it has to be in the radial direction relative to the axis of rotation. So we're going to call omega the magnitude of u there, because that describes the the magnitude of u is omega times r, since u serves as a tangential velocity with respect to the rotation, and we're going to say that the magnitude, of course, is angular velocity. Now, if we take the dot product of the velocity with itself, we've got three pieces. We've got the center of mass dot center of mass. We've got the center of mass dot the relative velocity, and finally just the u dot u. Obviously, this piece is what's going to give us the 1/2 mv squared, and this piece is pretty clearly going to end up giving us the rotational kinetic energy, and somehow this piece goes away. Let's see why. I mean, there's a little bit more to see here. So the total kinetic energy. So the total kinetic energy is just 1/2 m times the velocity squared, right? The total velocity squared. Total velocity squared has these three pieces. As I was saying, you can break this integral into three pieces. This first part, the integral over v dot u, and then finally the integral over. Notice that the omega is constant over the object because it's a rigid body. It's all rotating at the same speed, so I can pull that out of the integral. And then, of course, this integrates to big M, which gives us 1/2 mv squared. There's the translational part of the kinetic energy. I'm claiming this part's 0. And then this piece over here, well, that's the moment of inertia we've been calculating the last hour and a half of class, right? So there it is, 1/2 I omega squared. There's your translational and your rotational kinetic energy. Okay, so why is that middle term 0? If we notice, remember that the center of mass position is defined by 1/m times the integral of the position vector times dm, right? This is the weighted sum of position vectors over the object. And so if I calculate gamma minus r, integrate that over dm, well, that is, I can divide and multiply by 1/m, all right, like that. And if I do that, I get just dm over here. Notice because the m, sorry, my eyes are not working. Give me a second here. How did I get from here to here? Oh, I'm sorry. I was thinking I did this to both terms. I just did it to the first term, right? So it's just this piece, m over m. And then over here, if you go up there, if we what? What? I did read this earlier. It made sense to me earlier. I must not have looked at it right. Or not looking at it right now, I'm not sure. We can pull the r out because it's constant, right? So, I'm an idiot. So, listen, this is just, I'm just pulling I'm pulling r outside the integral here, right? Because it's constant, so that just leaves me integral of dm. And this piece is that piece. Great. So what we then have, this is literally the center of mass by this right here, okay? So we've got the mass times the center of mass minus, this is mass times center of mass. Well, that's 0. Okay, well, duh. And once you know that, you can take that formula and differentiate it. That's the next step, is if you differentiate that, this formula right here, if I look at v dot u, well, that's the integral of v dot d gamma dt minus v if you go back to how we defined little u. And as such, if I pull the time derivative out of the integral, because that's legitimate, and don't ask the math professors, but pull the ddt out of the integral, and that gives us gamma minus r in this context. How does it give us gamma minus r? V, because v is big dr dt, remember? Right, so big V is big dr dt, and so that's why we've got that r there. But this we already know is 0, so we've got the derivative of 0, which is 0. Fine. We finally showed what I claimed, which is that the part that comes from the relative, the dot product of the center of mass velocity with the relative velocity, that zeroes out. All right, great. So let's look at an example problem. I'm going to put this away because you guys should see me write something. Good grief. Do you guys like classes where all they do is just like point at a PowerPoint the whole time? No, it's pretty obnoxious, right? Yeah. So I try to keep this to a minimum in here. And again, I would ordinarily just try to derive those things, but I know my limitations today, so my apologies. So let us look at an example. Let's see here. So we'll do something like I just had up on the board. Suppose we've got an inclined plane. All right. And up here, we've got a ball. All right. And its radius is r. And it's going to roll down the plane. All right. And here it has velocity vf. All right. And let's say it's rolling without slipping, right? And it's going to start up here at height h. And let's let it start with let's let it start from rest. All right, so it's going to start at rest, and then it just rolls down. All right, it starts from rest. So and we're also going to assume that energy lost to friction is negligible, all right? So at this point, the question becomes, so it's rolling, right? And I just said it's a ball. I didn't really tell you what kind of ball it is. So now you guys get to choose. Would you like to make it a solid bowling ball? Would you like to make it a spherical shell? Would you like to make it like a wheel of cheese?
Make it a shell.
A spherical shell? All right, spherical shell it is.
Gotta take all the way down.
Sounds like harder options. You show some example of it, and you know how to do that.
They're all the same. So
Well, we tried it.
the more confusing way to make this problem is to not tell you what the shape is and make you find the moment of inertia from the motion. Yeah, a spherical shell, like tennis ball. Like
Keep jumping.
tennis ball or soccer ball or basketball, pretty much all your balls. All right, so they're mostly empty. I think. All right, so fun. So here's the deal. We have rolling without slipping means that Vf is equal to r times omega f. So r is the radius of the ball. As the ball rolls, if it's rolling without slipping, the tangential velocity and the angular velocity have to be related in this way. Why is this here? Okay. So now, so here's the deal. The energy, so we're not losing any energy due to friction, so we have the final energy and the initial energy are equal. But now there's a new player in the game. We have kinetic energy rotational and kinetic energy translational. So the translational kinetic energy is what we already talked about, 1/2 m v naught squared, right? Plus 1/2 I omega naught squared plus m, I guess big M gh is equal to 1/2 m vf squared plus 1/2 I omega f squared, right? Plus mg, the final h, right? In principle, this is what's going on, right? If the ball was rolling to start with, this equation would account for that, right? But we did, what did we give? I gave you, we made it easier, right? V naught is equal to 0. So this is given to be 0, right? And this being 0 means that that is also 0, right? If it's initially not going down the plane, it's also initially not rolling with any velocity, right? If it was rolling and it wasn't moving, that would mean that it's not rolling without slipping, it would be slipping. Okay, so long and short of it, we got ourselves an mgh. 1/2 big M Vf squared. What's my moment of inertia? Spherical shell, what was the deal? What did we say it was? Was it 2/3? Was it 2/3? Okay, so 1/2 times 2/3 mr squared, right? Omega f squared. And this was 0. Because we've defined the 0 for potential energy to be 0 on the plane because, well, that's what we always do. There's an m everywhere. We could cancel those, right? So let's divide by m. And did you guys notice what this is? What's this here? Two's baby canceling. This is Vf squared, is it not? Because I've got an R and I've got an omega, you multiply those together, you get a Vf, you got two of them, you got a Vf squared. So if I divide this by m, I just get GH equals to 5/6 Vf squared, which is to say that my final velocity is equal to 6GH divided by 5 square root. And there you go. That's the speed at which this mass is rolling without slipping if it starts from rest and just rolls down the plane. How would this change if it wasn't a spherical shell? What if it was my block of cheese? It's a cylinder rolling down. How would that go? What does it change? Nothing, except one thing, right? Right, so like this, you could make 1/2 mr squared, you know, for cheese wheel. You could make it mr squared for hula hoop. You could make it, what else do we got here? 2/5 mr squared for like bowling ball. Non-realistic. Right? Because actual bowling balls are not uniform density, are they? They've got this, you know, candy kind. They're like a gobstopper, right?
Like a bouncy ball that we're working with there.
Thank you. Bouncy ball. There we go. That'll work. All right.
Minus the balance.
Well, yeah. We're not going to bounce it. We're just going to roll it. The fun way to ask this question, in a slightly different way, is what if I tell you, here's a different way you can ask it. You can say, question, what is the moment of inertia for m, for the mass, given Vf is equal to, I don't know, the square root of, say, 7GH over 8, whatever. Make up your favorite number to put here, right? You could work this out as well, If you know the final If you know the final velocity, you can put that into here, and you can track back what the moment of inertia would have had to have been in order to achieve that result as well. That's another way to ask this question. But I think, oh, hey, what am I doing? The weekend has begun. Let me shut up. So, we will do more of these. Have no fear.